So good afternoon, students. Good afternoon once again. In the previous class, we started the pulse modulation schemes. The pulse modulation scheme is the modulation which is going to be modulate a message signal with the pulse train. Okay, pulse train. So the difference between analog modulations is amplitude modulation, frequency modulation, and phase modulation, and pulse modulation. That amplitude modulation, frequency modulation, phase modulation signals that message signal is a continuous signal, carrier signal also continuous signal. There is in the pulse modulation scheme, message signal is a continuous signal, and carrier should be a pulse. Carrier should be a pulse. That's why the pulse amplitude changes according to modulated signal, that is pulse amplitude modulation. Pulse width changes according to modulated signal, that is pulse width modulation. Pulse position changes according to modulated signal, that is pulse position modulation. Likewise, you have to discriminate the pulse modulation schemes. There is pulse amplitude modulation, pulse width modulation, pulse position modulation. That means the parameter of the pulse, that is either it is the amplitude, either it is the width, either it is the position of the pulse changes according to the modulated signal changes. That is pulse modulation schemes. So before going to the pulse modulation schemes, you have to see that how the important concept, that is conversion of analog to digital. Analog to digital. Why you go for the analog to digital conversion? Because of the digital domain, there is lot more advantages are there. So the digital modulation scheme is very much error-free, and it should be occupy less power also. So whereas in this analog signal transmission, if it is required 30 to 60 dB power, but in this digital domain transmission, the same, that is 10 to 12 dB. How much the power is reduced there now. See, that is the advantage of digital modulation. The digital modulation scheme is accurate and error-free and less power also used. Less power means less bandwidth also used. So that's why you can convert analog domain into digital domain. If you want to convert analog domain to digital domain, you require some sort of procedures are there. Among the procedures, there should be one of the method is sampling. One of the important method is sampling. Already you see that sampling theorem. So the sampling theorem means, so the sampling theorem says once again define that. So we consider the fundamental principle of digital communication, the sampling theorem. So that amount signal is a modulated signal or band signal with the baseband signal. So having the frequency is FM, and the time description of this amount signal. So that is the regular intervals of the time separation of the amount signal is nothing but samples. So the regular intervals of amount signal with the time intervals. The time intervals having TS less than or equal to 1 by 2FM. TS, the sampling time for the amount signal, and there is less than or equal to 1 by 2FM. So this is the signal is periodically sampled at every TS seconds. The TS is the sampling period that is periodically sampled at every regular intervals of the time, that is TS. The TS should be less than or equal to 1 by 2FM is the sampling theorem. Students, we note that the sampling theorem, TS less than or equal to 1 by 2FM, or Fs greater than 2F, or Fs greater than 2F. Fs means 1 by TS. Fs is sampling frequency, but TS is sampling time. So it has, after the conversion of samples, M of t signal is converted to M of NTS. M of t signal is converted to M of NTS. So M is integer value. The TS is sampling time. So now the time TS is called sampling time. The time Ts is called sampling time. So note that the theorem requires the sampling rate be rapid enough so that at least 2 samples are taken during the course of the period corresponding to the highest frequency spectral, especially spectral. That is Ts greater than 2 1 by 2f. So now let us see that procedure. If some amount signal is there, that is continuous signal, that is given to multiplier, and another signal nothing but a periodic pulse train. Periodic pulse train it is. Because the SFT, that is a periodic pulse train, having the dt is the pulse width. Dt is the pulse width. This is the uniform periodic signal, periodic pulses having the unity magnitude. So that is given to another end. These MRT signal and SFT signal are given to a multiplier. The multiplier output should be SFT into MRT. This is an output. Now we can say that a sampled signal time instant, Ts, 2Ts, 3Ts likewise now. Sample Ts having the magnitude continuously varying with the MRT signal. What the MRT signal magnitude that impose on the sample pulses. Impose on the sample pulses. So this procedure may also called as a pulse amplitude modulation. Pulse amplitude. Because of these pulses, the amplitude is there. According to the pulse, amplitude of the modulator can impose on the samples. Impose on the this is consideration. The baseband signal M of t, which is to be sampled in the shown in figure. The periodic pulse train S of t is unit magnitude and period Ts is shown in the figure. The samples are narrow, very narrow samples are there, having width of dt. The two signals M of t and S of t are applied to a multiplier as shown in the figure, okay, which they yield as output of product of S of t and M of t. So this product is shown in the figure also. So now M of t sampled at the occurrence of each pulse. Okay, so it is when the pulse occurs, the multiplier output has the same value as done in M of t. See this statement. That is, when a pulse occurs, the multiplier output has the same value as does M of t, and at all other times the multiplier output should be 0. What it indicates that where S of t there, then the multiplier output is M of t having the magnitude for M of t there. So all places the magnitude should be the 0. That means there is no signal. ఎక్కడైతే S of t signal ఉంటుందో then M of t signal is imposed on the S of t. So S of t signal లేనప్పుడు the magnitude should be the 0. Magnitude should be the 0. So this is seen this mathematical constraint. So let the signal S of t be periodic. S of t be periodic with the period Ts. And the Fourier expression of this S of t signal is, so where this is from the equation S equal to dt by Ts. This is Fourier expression, Fourier series expression. Dt by Ts, dt the width of the pulse by Ts plus 2 dt by Ts into cos 2 pi 1 by t by Ts plus cos 2 into 2 pi t by Ts plus cos 4 into 2 pi t by Ts, so on. So this is the S of t, a pulse train having the Fourier expression of this. Please we know that the first equation 1 is S of t signal equation 1. S of t is applied Fourier expression, Fourier series expression. That is dt by Ts plus 2 dt by ts cos 2 pi t by ts plus cos 2 into 2 pi t by ts plus cos 4 into 2 pi t by ts like this. No? So for the case ts is equal to 1 by 2fm. For the case ts is equal to 1 by 2. So if you substitute in the place of ts 1 by 2fm, the product s of t and m of t there. So substitute ts is equal to 1 dt by ts into m of t plus dt by ts into 2 into m of t cos 2 pi 2 m of t plus 2 m of t cos 2 pi 4 fm of t plus cos 2 m of t into cos 2 pi into 6 fm of t like this. So it is the frequency is 2 fm, 4 fm, 6 fm like this. This is a multiplied signal with Fourier expression. Multiplied signal with Fourier expression. Now, so we now observe that the term in the series, aside from the constraint factor, the signal m of t itself, again, aside from the multiplying factor, the second term is the product of m of t and sinusoid of the QF. Okay. This product then a double sideband suppress carry. This product may called as double sideband suppress carry. So that means this is the product of S of t and M of t that gives double sideband suppress carry signal, DSBS signal. Why? Because so DSBS signal can be generated by product multiplier. DSBS signal can be generated by product multiplier. Product multiplier may also called as balanced modulator. Product multiplier is called as balanced modulator. So that the balanced modulator should be DSBS signal. Balanced modulator should be DSBS signal because of balanced modulator can also the product multiplier. That's why the M of t and S of t product gives DSBS signal. So and the carrier frequencies are 2fm, 4fm, 6fm like that. What is fm? The signal frequency, highest signal frequency. Now this is M of t signal is applied. That is 0 to fm, and the product of Fourier series of M of t that gives fm, 2fm, 4fm, 6fm like this. Fm, 2fm minus fm, this fm. So 3fm minus fm, this fm like this. So center frequency should be the 2fm, 4fm, 6fm like this. So this is process of the multiplexing of S of t, the Fourier series expression. This is the spectral components. These are the spectral components. Spectral components occur at every of 2fm, 4fm, 6fm like that. The span is 2fm. The span is 2fm. That is positive side is fm, negative side is fm. Fm plus fm, that is the shift to the 2fm. Okay, so that is the expression of Fourier series multiplication. This is also called as DSBS signal also. Okay, now already you know the previous class also discussed this concept is 2fm minus fm, that's 3fm, 2fm plus fm, that is 3fm, the span between fm to 3fm, that is the 2fm is the center frequency. So altogether, so this is the expression of if suppose fm is the maximum frequency and the active spectral component start at fs minus fm. Fs minus fm. So there the gap between fm and fs minus fm, there is a gap. So this gap may called as guard band. This gap may called as the guard band. So if the guard band is provided at fs greater than 2fm condition, and the guard band is provided at fs greater than 2fm condition. So actually this relation may called as sampling theorem. This relation may called as sampling theorem. So at the sampling theorem, the recovered samples, the recovered modulated signal from the samples in this Fs greater than 2Fm condition only. The recovered amount of the signal from the samples. The recovered amount of the signal from the samples in this Fs greater than 2Fm condition only. Because of there should be a guard bands. There should be a guard bands. So if the guard bands are there, the chance of getting amount result from the samples. Then the guard bands are allowed. Guard bands are allowed. So and also another thing is guard bands are used to protect the signal. Guard bands are used to protect the signal. That's why the name itself says guard band. Guard band. Guard band is used to protect the signal. So at this we're able to get the amount of signal from the samples accurately. Okay, there is no loss of the signal. So accurately can get the amount of signal from the samples at the receiving side. At the receiving side. So at the sending side, can send the signal after sampling to this channel. At the receiving end, what to do? From the samples, you can recollect the amount of signal. Amount of signal is the transmitting end. So amount of signal is the receiving end also. So meanwhile, the samples are propagating. So now the samples are propagating, and at the receiving end, you got the amount of signal from the samples by using this formula only. So that's why this formula Fs greater than 2Fm condition called as sampling theorem. So another relation also there. If Fs less than 2Fm, what happens? If less than 2Fm, what happens? Fs less than 2Fm, then there should be a overlapping Fs. So one sample is overlapping to another sample. First sample is overlapping to second sample is overlapping to third sample, like this. So overlapping of. So this overlapping called as aliasing effect. So overlapping effect, at this condition, unable to recollect amount of signal from the samples. Unable to recollect amount of signal from the samples. That is the condition of Fs less than 2Fm. That's why this is oversampling. This is the oversampling. So Fs greater than 2Fm is undersampling. So Fs less than 2Fm is oversampling. In the undersampling, able to get the amount of samples. Oversampling are able to recollect the amount of from samples because of aliasing effect is there. Aliasing effect means overlapping of samples. That is aliasing. Okay. So now there is one more thing is that Fs is equal to 2Fm condition. Fs is equal to 2Fm condition. So Fs is equal to 2Fm condition. Nothing but the Nyquist Fs equal to condition called as Nyquist rate. Okay. So now. So all this thing is already discussed in the class. So this is the minimum sampling rate known as a Nyquist rate. What is the minimum sampling rate? Fs is equal to Fm or Ts is equal to Fs is equal to Fm or Ts is 1 by 2Fm. So that is Fs is equal to Fm condition. That is minimum sampling rate. So that is known as Nyquist rate. Now this is the condition of the commutator and decommutator used to propagate by single channel. As samples are generated for each signal, there are different signals are there. So in this example, there are 5 signals: M1, M2, M3, M4, M5. So these 5 signals are sampled and transmitting to a single channel. At the receiving end, we have to use the decommutator. The speed of the commutator and decommutator should be the coincidence. So then only can get the received signal accurately. If the commutator speed and decommutator speed is not matching, then you are misunderstanding that if you first signal sample, then you got the second signal sample or the previous signal sample. So not the exact sample. So that is the case when the speed of commutator and decommutator differ. If the speed of comparator becomes the same, then M signal is transmitting, M signal sample is received. M2 signal is transmitting, M2 signal is received. The speed of the commutator and decommutator is the same. So commutator is at the transmitting end, decommutator is at the receiving end. Okay, this is a let an example. There is M1 and M2 are the two signals are considered here in this example. So it has sample 1 and M2 has sample 1. Channel 1 channel 2 means M1 has the first sample, M2 also the first sample. This is the set of first samples. So this is a set of second samples. This is a set of third samples. This is a set of fourth samples. This is a set of fifth samples. Likewise, that means fourth sample or fifth sample or sixth sample, whatever the sample it is, the samples are occurred between first samples of those signals. Okay. First sample of first signal, first sample of second signal. If it is any third signal is there, that is the first sample of third signal. Like that. So these are the samples are individual signal samples are composed and then going to be propagated. So we observe that train of pulses corresponding to the samples of each signal are modulated in amplitude accordance with the signal itself. Okay. The amplitude can be varied. Accordingly, the schema of sampling is called pulse amplitude modulation. Pulse amplitude modulation or abbreviated as PAM. Okay. Now, let us go for sample. Let us go for natural sample. It was convenient for propose to introduce the same basic idea to begin our discussion of time multiplexing by assuming instantaneous computation and decomputation. Instantaneous decomputation is imposed here. Such instantaneous sampling, however, is hard feasible. Even if you are possible to construct switches which could operate in an arbitrary short time, we would be disencouraged to use them. The reason is that instantaneous samples at the transmitting end of the channel have infinitely so in this concept the signal has to be transmitting with the instantaneous instantaneous times. Okay, let an example. So there is M of the signal, and S of t is there. S of t has some sort of delta span is there. The width of the pulse, width of the pulse is the delta. The delta. Sorry, the is tau. The value is tau. Where dt is the small, the tau is the large, somewhat large. Now the time is ds. So M of the signal is considered. So samples are considered. Now if you multiplex M of t and S of t, M of t and S of t, then what happens it is. So now you can observe the first sample is occurred. This is the first sample. The amplitude of the first sample is same as the M of the signal. The second sample, the amplitude of the pulse is same as the M of the signal amplitude. And third sample is there, the amplitude is same as the M of the signal amplitude. Fourth sample is there, amplitude is same as the M of the signal amplitude. Fifth sample is there, M of the signal amplitude is same as the M of the signal amplitude. That means the amplitude of the SRT, that is the samples, are changes accordingly. The amplitude of the SRT changes according to modulated signal change. That is M of the signal changes. Modulated signal in the sense M of the signal. Okay. So this is not but pulse amplitude modulation. measurement pulse amplitude modulation. Yes. To prove this, we know that sampling wave SRT, that is the pulse strain, and tau is the pulse duration. Tau is the pulse duration. So now SRT is equal to tau by Ts plus 2 tau by Ts, C1 into cos 2 pi T by Ts, C2 into cos 2 into 2 pi T by Ts, plus C3 into cos 4 into 2 pi T by Ts likewise, where the C is a constant given as a sync signal sin tau by tau Ts. That Cn is the sync signal. Sin x by x now sync signal now. So now Cn is equal to sin n pi T by tau by n pi tau by Ts by n pi tau by Ts. That is Cn. Now you can observe that. So the various harmonics are generated there. So the harmonics are, that is the sample base signal with S of t and M of t. Then S of t and M of t with T by Ts, tau by Ts and M of t, plus T tau by Ts and M of t into C1 cos 2 pi 2 Fm of t plus M of t C2 cos 2 pi 4 Fm of 4 Fm of t plus so on. So therefore, as in instantaneous sampling, a low pass filter with cutoff frequency FM, cutoff frequency at FM, will deliver the output signal S naught of t given by S naught of t to T by tau by Ts and M of t. That is the output of signal of the filter, that is the low pass filter, and the cutoff frequency PFM. That is output S naught of t is equal to tau by Ts and M of t. So which is the same as given by the first term of the previous expression, where the starting of sampling theorem, except dt is equal to replace with tau. Dt is replaced with tau. The dt is the small duration of pulse, whereas tau is the somewhat large duration of pulse. This is a pulse amplitude modulation. The pulse amplitude modulation. So natural sampling also called as pulse amplitude modulation. Now next another sampling is flat top sampling. Flat top sampling. In the sampling, there are two types. One is natural sampling, another one is flat top sampling. The flat top sampling, the pulses of samples, pulses of samples in the figure shows the top of the sample should be the same. The top of the sample should be flat. So samples are varied in according to moderate signal changes. Samples are varied in moderate signal changes. But the top of the sample should be the flat. Top of the sample should be the flat. Okay. The waveform is likewise. So now S of t signal and M of t signal interact. There S of t amplitude changes, but the S of t top should be the flat. Top should be the flat. So now the M of t signal dotted line now. M of t signal glazing the first sample leading edge, the amplitude touch, sample leading edge, the amplitude touch likewise. That is, glazing of the amplitude should be the beginning of the sample. One limitation is there. Whereas in the natural sampling, flat top sampling, one advantage is there, and there is limitation is there. So advantage of flat top sampling or natural sampling is top of the sample should be flat, then easy to encode the signal, and the digitization is easy because of the top of the sample should be flat. Okay, and also the noise is less compared to natural sample. Noise is less, and the limitation is it affected by aperture. So effect of the aperture effect is done in this flat top sample. Aperture effect is done in the flat top sample. What is the aperture effect? What is the aperture effect? So the aperture effect means aperture effect is not on the aperture effect. Aperture effect means, let us see, there is a marked signal having the decoding side. So the MFT has the flat top. Now, if you have to an idealized spectrum of response signal, this idealized spectrum, that is the flat, and the B bit is the spectrum of signal with the instantaneous sample. Is the sampling signal at 0 to FM, and Fs, that is sampling frequency, to FM, and Fs minus FM is the end, and Fs plus FM is another end. Fs minus FM, Fs plus. So between Fs, FM and Fs minus FM, there is gap, and you have to recover the signal. So then the spectrum of sin x by x, that is sync signal. The spectrum sin x by x, the sync signal, with x is equal to omega tau by 2. So of the distortion factor, where x is the distortion factor, that should be omega tau by 2. So that is the distortion factor. That is not the aperture effect. You know, the aperture effect introduced by the flat top sample. The flat top sample is the aperture effect. So see that. So the CBT is just that the flat top sampling, if your recovered process is done, record process is done, the magnitude of the signal going to be decreased along with the time. So along with the frequency. So frequency goes on increases, the magnitude goes on decreases. The first one is the unity. After that, going to be decreases slowly. So if you recover the signal, what happens is magnitude should be the first sample is the same, somewhat better. Second sample is somewhat reduces, and third sample is further reduces, fourth sample is further reduces like this. So the reduction of the amplitude of the samples, at the recovered process may called as aperture effect. So that means they are unable to recover the samples at higher frequencies. That is what aperture effect. You see that the first sample is somewhat a little bit same, but small fraction of error is there. And second sample is the fraction of difference is increases. So the third sample is further decreasing of the amplitude. So likewise, this decreasing of amplitude may called as aperture effect. This decreasing of the amplitude is may called as aperture effect. So this is the aperture effect. Aperture effect is done in only the flat top sampling. Aperture effect is done only the flat top sampling. Now see this. The drawback of here. What the drawbacks of here? What are the drawbacks of here? So bandwidth required for transmission of the AM signal is very large. Bandwidth required for transmission of AM signal is very large in comparison to maximum frequency present in modulating signal. Once again, read out. The bandwidth required for transmission of AM signal is very large in comparison to maximum frequency present in modulating signal. And second one is, since AM pulses varied in accordance with modulated signal, Since PAM pulses vary in accordance with modulated signal, therefore interference of the noise is maximum. Interference of the noise is maximum. So in the PAM, interference of the noise is maximum because the amplitude varies now. So the third one is amplitude of the PAM signal varies. Thus, also varies peak power required by transmitter. Amplitude of PAM signal varies. This also varies peak power required by transmitter. Now, there is pulse time modulation. Whereas you see the PAM pulse amplitude modulation. So, and other different modulation systems are there. Other different modulation systems. Pulse time modulation. There are two types of pulse time modulation schemes. One is pulse width modulation, another one is pulse position modulation. This pulse width modulation, another is pulse position modulation. With the pulse width modulation, so it is also known as pulse duration modulation. It is also known as duration modulation. So the width of the modulated signal, so the width of the modulated pulse varied in accordance with amplitude of the modulation. So the definition. So it is also known as pulse duration modulation. So the width of the modulated pulses varied in accordance with the amplitude of the modulated signal. Now the width of the pulse varies according to modulated signal changes. That is pulse width modulation. So see the pulse width modulation diagram. See the comparator. For the comparator, the amount of signal is given. That is modulated signal. Another is known as sawtooth wave. Sawtooth generated, and that is given to another part. Now the comparator compare these two signals. That output should be the PAM. Output should be the PWM output. Output should be PWM output. So now see that a sawtooth generator generates a sawtooth signal of frequency f. Therefore, sawtooth signal in this case is sampling signal. The signal can act as a sampling signal in this case. It is applied to the inverted terminal of comparator. And modulated signal is applied to the non-inverting terminal of the comparator. However, amount of signal amplitude is higher than the sawtooth signal. That is, the amount of signal is applied now. That is, amplitude is higher than the sawtooth signal. The comparator output will be high. Otherwise, output is low. So now the comparator output is high. The comparator output will be the high. Otherwise, output is low. The resultant output waveform as shown here. So now you can see that there is comparator. Comparator have the two polarities, the positive and negative. At the positive polarity apply amount signal, and negative polarity apply the sawtooth signal. So now the amplitude of the amount signal is greater than the sawtooth signal. So now there should be interaction. See this waveform. This is soft signal or amount signal. Now the sawtooth signal is there. Sawtooth wave signal is there. Sawtooth signal is nothing but like a ramp signal. Like a ramp signal. So now the interaction takes place. So where amount signal and sawtooth signal interacted. So this is the interaction. This is interaction. This interaction. So this interaction. This is interaction. This interaction. So where the interaction of the amount signal and sawtooth signal, there this first pulse is there. The first pulse is there. Then this is the second pulse. This is the third pulse. This is the fourth pulse. This is the fifth pulse. This is the sixth pulse. So students, we will draw this sawtooth waveform. Draw the sawtooth waveform and draw the dotted lines below where the interaction point takes place. ఎక్కడైతే మనకి sawtooth waveform కి SRK సిగ్నల్ కి ఇంటరాక్షన్ ప్లేస్ ఉందో ఆ ఇంటరాక్షన్ ప్లేస్ దగ్గర సిగ్నల్ డ్రా చేయండి. When the signal drawn, what happens is width of the output pulse. The width of the pulse varies. The width is first width is somewhat, second pulse width is somewhat, third pulse width is somewhat, like that. Now this is pulse width modulation. Now can we say that the pulse width varies according to the modulated signal changes. Pulse width varies according to the modulated signal changes. So this is pulse width modulation. Pulse width modulation. Okay. So students can the next class go for pulse position modulation and remaining concepts. So please go to this material and some sort of analysis also there. Please go to that. Okay. So thank you, Anand.